Well, so we will continue with our discussions on the flow regime dependent analysis of two phase flow. So, in the last class we had discussed the bubbly flow pattern, and I told you the range of bubbly flow patterns that we can have, and definitely for each different ranges we are going to have different values of u infinity and n, and according to that actually then what we did was we proposed different regimes based on some non-dimensional groups, and then based on those particular regimes we proposed different values of u infinity and n, which can be incorporated in the basic expression to find out J21, isn't it. So, we knew already that J21 this is equal to u infinity alpha into 1 minus alpha whole to the power n. So, therefore, in order to find out J21 we need to find u infinity and n. So, what we had proposed was we proposed that this u infinity and n they are different for different flow patterns, and I had proposed the set of a particular in a tabular form. I had proposed the different regimes where different values of u infinity and n they are applicable, and those particular regimes were based on the some particular non-dimensionless groups. One was definitely the bubble Reynolds number, the others were G1 and G2, two particular dimensionless groups with liquid and liquid properties particularly incorporated in them. Okay. So, after that what we did, and once we could so we found out that in order to find out J21 we need to know u infinity. Okay. So, therefore, and we found out that the expressions of u infinity that I had put up on the table, they were mostly a function of their bubble radius or the bubble diameter. Okay. It was a function of RB. So, we next went to discuss the different ways of finding out RB. We found out that the bubble equivalent diameter or the bubble equivalent radius, that is a function of the way the bubbles are produced. They might be produced through an orifice, they might be produced or they might be detaching themselves from a blanket of vapor which has been formed over a porous plate or over a heated surface, and from there they can detach depending on the way they are formed, their equivalent bubble radius can be determined. Once we can determine them, we can then again incorporate them in u infinity. Certain other small things also we had discussed in the last class. Now, in today's class I will be taking up the slug flow pattern. Now, I have already discussed slug flow pattern in great details in one of the previous classes, and I would just like to show you the schematic of the slug flow pattern which we had already discussed. We found out that the slug flow pattern is a unique flow distribution which is characterized by a periodic appearance. That means, if you look at any one particular cross section, say suppose you look at this particular cross section, we find that at one particular point it will be almost filled up with gases for a particular interval of time, and after that it will be filled up with a bubbly mixture, and then again pure gas with a thin liquid film, and again a bubbly mixture. So, this particular periodic appearance makes slug flow very unique in several respects. Okay. Now, the best way to analyze the slug flow pattern, firstly, as we know that it's I have already told you its importance has been enhanced particularly with miniaturization, because in micro systems and in millimeter size systems we find that slug flow occurs over a very wide range of phase flow rates. Under such conditions we usually do not get bubbly flow. So, therefore, as we reduce the pipe dimension we find that slug flow pattern becomes much more prevalent. Number 1. Number 2, we find that as we reduce the diameter, the tendency of the liquid slug to become aerated also decreases. And more or less for very small pipe dimensions, say millimetric or the micrometric channels, we find that more or less slug fluid is characterized by periodic appearance of Taylor bubbles and unaerated liquid slugs, as I have shown in this particular figure. This is an ideal slug flow in a vertical tube, and usually we find that when we go for narrow channels we get something of this sort. Now, for a vertical pipe, the best way of analyzing slug flow is, because since lot of things are varying, What are the things that are varying? The gas phase, it is in two different type of forms. One is the Taylor bubble, the other as small bubbles in the liquid slug. The liquid again in two forms. One is as a continuous liquid slug, which may or may not be aerated, then as a very thin liquid film, annular film between the Taylor bubble and the pipe wall. Again, for what are the other things that we notice? The flow of liquid, the flow direction of liquid also changes at a particular cross section. Why? Because the liquid slug, it is moving up, the liquid moves up in the liquid slug, but in the Taylor bubble region the liquid portion moves down. So, therefore, we find that everything, the void fraction, the pressure drop, even the velocities, everything they change periodically with time, and therefore, it appears to be quite complicated, and therefore, for this analysis the most convenient thing which is done, since everything changes over a particular cross section. So, therefore, if we concentrate on a particular cross section, then with time it keeps on changing. So, we have to take into account the temporal variation. In order to avoid this, what we do? We divide the entire slug flow passage or the entire flow passage into unit cells, just like I have done in this particular slide. We divide the entire flow passage into a large number of unit cells. For each unit cell, it comprises of a Taylor bubble and a part of the liquid slug above it as well as below it. So, therefore, what happens if we can find out the void fraction of this particular unit slug, we can say this is the void fraction of the entire channel, is not it? And once we can find out the void fraction, we can find out the pressure drop, we can find out the other hydrodynamic as well as other parameters of slug flow. So, therefore, we find that the analysis becomes considerably simplified if we can assume that the entire flow passage comprises of unit cell, where each cell is made up of a single elongated bullet shaped axis symmetric Taylor bubble and some liquid portions above and below it. And naturally, as I have already mentioned before, we have been also considering axis symmetric one dimensional flow with constant gas and liquid properties in this particular case. And then in that case, once we know the void fraction here and we know the total number of unit cells in the entire flow passage, then we can find out all the requisite parameters. Okay. The other thing to start with, what we do is we assume the pure liquid slugs. Pure liquid slugs means unaerated liquid slugs, which we usually do not get under ordinary circumstances. Under ordinary circumstances, as I have already mentioned, what happens just when the liquid, it is flowing down from here and it meets the upward flowing liquid slug, a wake region is formed. This wake, due to this formation of this wake region, what happens is good amount of gas is sheared from the tail of the Taylor bubble and they distribute as small bubbles and they resemble the bubbly flow pattern in the liquid slug region. Usually we find that the concentration of bubbles are more near the just below the tail region, and then after that more or less we can assume a uniform distribution of the liquid bubbles, of the gas bubbles. Now, what happens when this particular liquid again begins to fall as an annular film between the Taylor bubble as well as the tube wall, then we find usually the liquid film dimension is much less than the dimension of the dispersed phase. Therefore, usually bubbles are not carried in the liquid film. Okay. So, therefore, pure liquid flows as a thin annular film between the Taylor bubble and the tube wall, and when this meets the liquid slug below, then a good amount of aeration occurs under normal circumstances. Now, to start with, see, this analysis has gone to a well researched extent because slug flow is so very important. Now, to start with, since I do not have much time, I cannot spend much time on this. So, we will be doing the simplified analysis, and after that I will just discuss what are the ways by which we can incorporate the other factors which will make the model much more realistic and much more applicable for practical situations. So, what is the thing that we the thing that we first consider? We consider ideal slug flow, where we have broken up the entire flow passage into large number of unit cells. Now, in each unit cell, if you observe, what you find a single Taylor bubble. This Taylor bubble is rising up at a velocity ub, okay, where u bubble is nothing but the u gas, because the entire gas phase is confined as Taylor bubbles in the slug flow pattern. So, ub is nothing but the it is nothing but ug for the present case where we have assumed unaerated liquid slugs. Remember this, if we had assumed aerated liquid slugs, then definitely we could not have said this. Okay. So, therefore, we find that this rises up at a velocity ub, which is equal to ug, the in situ gas velocity. Now, at the bottom of the passage, air and water, or rather gas and liquid, are introduced at flow rates QL and QG. Okay. And this particular, these two phases, they keep on flowing up through the flow passage. Now, try to understand one thing, since the from continuity of mass, what do we get? Suppose we have a flow passage where this is introduced at QL, this is introduced at QG. So, at the entry we have J, which is equal to the overall volumetric flux is equal to QL plus QG by A. Okay. Inside the passage, maybe we have some sort of Taylor bubbles, liquid slug, and again another sort of Taylor bubble. Now, suppose we take any particular cross section, the overall volumetric flux must be same. So, therefore, the liquid in this particular portion, this should also rise with a volumetric flux J, where J equals QL plus QG by A. Okay. And in this particular portion, if we assume that the entire gas in the Taylor bubble rises at the same velocity, then this will rise at a velocity u bubble, and the liquid will be flowing here, flowing downwards at a velocity u f, or the u film. Okay. Now, in this particular case, try to understand one thing. Now, suppose we consider the drift velocity. Remember one thing, usually till now we have been using u1, u2, subscripts 1 and 2. Here, since we are considering gas liquid slug flow, I will be using subscripts G and L. You can use whatever suits you best. If it is liquid slug flow, then in that case definitely 1 and 2 has to be used. So, whatever suits you, you can use. I will be just using G and L subscripts here, simply to show that we are discussing gas liquid slug flow. Now, remember one thing, gas liquid slug flow in vertical and horizontal tubes have different characteristics. Why? What is the basic difference? If you observe the slug flow which I have shown in the vertical and the horizontal tube, you find that the basic difference is, here the slug flow pattern, although it has temporal variations, it is axisymmetric. In this particular case, it is distinctly asymmetric. So, therefore, the other thing is, here the gas bubbles, they rise due to buoyancy. Here in the horizontal tube, we do not expect any buoyancy to exist. So, therefore, it is quite understandable that a different physics should govern slug flow in vertical and horizontal pipes. So, therefore, what we will do? We will be primarily discussing slug flow in vertical pipes, because slug flow is more commonly encountered in vertical pipes, and after we have finished discussing, we will take a brief discussion on horizontal slug flow as well. Remember, whatever we have discussed for vertical slug flow cannot be directly applied to the horizontal case. Yes, it can be applied where? Under micro channels. Why? Because moment we go to lower and lower dimensions, surface properties become more important and gravitational force gets a back seat. So, therefore, under that condition we find that the flow patterns are independent of inclination, and we find actually that there is not much difference in the flow distribution in a horizontal as well as a vertical tube. We find in both there is no stratification for micro channels, or in for say 1 millimeter, 2 millimeter channels. We usually get slug and annular flow patterns predominantly in both the cases. Okay. So, under that condition it is different, otherwise the analysis for vertical slug flow cannot be extended in a straightforward manner for horizontal slug flow. So, to start with, we start the analysis for vertical slug flow. Now, in this particular case, what do we find? We find that the liquid ahead of the bubble, that moves up at a velocity j. Try to understand this concept very well. So, therefore, the drift velocity of the bubble, say drift velocity of the Taylor bubble, which can be written as UGJ or U2J whatever, that is equal to UG minus J. Agreed all of you? Again this is equal to UB minus J, assuming that the entire gas phase rises up as the bubble and all the gas in the bubble rises at the same velocity. Okay, so, from this particular expression what do we get? We find that bubble dynamics, which is governed by UGJ, that is a function of what parameters? It is a function of J, volumetric flux, it depends upon J, isn't it? If it depends upon J, it should also depend on the velocity profile in the liquid slug, yes or no? Isn't it? It should depend on the velocity profile, and this velocity profile, it is governed by which parameter governs the velocity profile, can you tell me? The velocity profile in that case, it is governed by what are the factors which govern the velocity profile? See, it can be parabolic, it can be flat. What decides the velocity profile? When do we have a flat velocity profile and when do we have a parabolic velocity profile and so on and so forth? Yes? Does it depend upon Reynolds number by any chance? It should depend upon Reynolds number, yes or no? Okay. So, therefore, velocity profile in the liquid slug, this is again a function of REJV, right, which is d or rather dj rho L by mu L, isn't it? On what other factors it should depend? It should depend upon the conduit characteristics, it should depend upon the fluid flow properties and so on and so forth, isn't it? So, therefore, we find that more or less your uj, it should depend upon J, the corresponding velocity profile in the liquid slug, then it should also depend upon bubble length and pipe geometry. Usually it depends on these factors, isn't it? Because bubble dynamics means the rise of bubble with respect to the surroundings. So, therefore, that should definitely depend upon the liquid which is flowing ahead of it, because depending on that velocity the bubble will rise faster or slower. It should depend upon the profile. Why should it depend upon the profile? Suppose it is the parabolic profile, the bubble tip is located at the center, then in that case it will not rise at the average volumetric flux, but will rise or it will be affected by the center line velocity, isn't it? So, therefore, that depends upon the velocity profile. Then it should depend upon the bubble length, it should depend upon the pipe geometry, it can depend upon the fluid physical properties, etc., etc. And again we find on what does this J depend? This J depends upon the wake effect from previous bubble, because whatever the previous bubble was there, there is a wake behind the bubble due to the falling of this liquid film and mixing here, there is a wake effect. So, therefore, if the liquid slug is not large enough, this wake effect will affect this bubble, and anyhow this wake effect will affect the liquid slug here. So, the J with which the liquid slug is rising, that will be influenced by here. So, therefore, J is affected by the wake effect from preceding bubble. Then pipe roughness, you can say, naturally pipe roughness, it gives the interfacial shear, sorry, the wall shear and the Reynolds number, isn't it? So, therefore, we find that if we compare whatever we have written, that bubble dynamics is a function of volumetric flux, velocity profile in the liquid slug, bubble length, pipe geometry, and since it depends upon J, it will also depend upon the wake effect from the preceding bubble, pipe roughness, Reynolds number, etc. Therefore, what do we find? For a particular system, say when the fluid properties, pipe geometry, everything it is constant. Under that condition, your bubble dynamics, which is mainly governed by the drift velocity, drift flux, etc., that should be a function of J and certain other parameters, but primarily a function of J. It does not depend upon the individual fluxes JL and JG. Do you agree with me? It depends upon the total J, because the liquid ahead is moving with J. It does not depend upon the individual flow rates JL and JG. Again, if you observe, you find that it does not also depend upon alpha. Why does it not depend on alpha? Because from here what we observe, that see the gas viscosity density, it is much negligible as compared to liquid viscosity density. Okay. Therefore, gas inside this bubble can be assumed to be at a constant pressure. Okay. The curvature is constant, more or less we can assume it to be a cylinder. Okay. So, therefore, it is a uniform cylinder, the curvature is constant. Therefore, this entire surface, it can be assumed to be a region of negligible shear, is not it? So, therefore, no matter how big the bubble is, it is not going to affect the bubble dynamics, because this entire region can be taken as a region of constant pressure with negligible shear. So, therefore, whatever shear is occurring, that is occurring between the liquid film and the tube wall, and if it is bigger, then in that case what we find? We find that maybe lesser number of bubbles will be, or lesser number of unit cells will be there, but in each particular unit cell this situation is the same, is not it? So, therefore, we find that considering the slug flow characteristics with unaerated liquid slugs and axisymmetric vertical flow, we find that the bubble dynamics, it is a function of J only. It does not depend upon the individual fluxes JL, JG, and it also should not depend upon alpha. Okay. It should primarily depend upon J and certain other factors. For a particular system under particular flow conditions, it depends on J only. Well, so this we have got by considering slug flow characteristics. You agree with me, all of you? Again, from drift velocity or from drift flux model, what do we get? Let us consider the drift flux model. Now, from the drift flux model, if you remember, what did we get from the drift flux model? We obtained, if you remember, J21, in this case it is going to be JGL, that was a function of alpha for a particular system. Do you remember this thing we had obtained there? And that is why from here we said that JGL equals to U infinity, and from there itself we had written down this particular expression. So, it was a function of alpha only. If JGL was a function of alpha, then naturally your UGJ, this should also be a function of alpha only, yes or no? Try to understand, I am speaking quite contradictory things. So, see if you are understanding what I want to say or not. Basically, by considering the slug flow dynamics, what do we get? We find that the slug flow dynamics is primarily governed by the bubble dynamics, the rise, the characteristics of the bubble. Now, by considering the ideal slug flow, what did we get? We find that the bubble dynamics for a particular system, it is governed by overall volumetric flux. It does not depend upon the individual fluxes, it does not depend upon alpha, because the bubble is considered to be a region of constant pressure with negligible interfacial shear. Agreed with me? So, if at all it has to be a function, it is a function of J only. Now, if we consider the drift flux model, because we are considering your drift velocity and the drift flux. If you remember drift flux model for negligible wall shear, okay, that was one particular condition. For vertical slug flow, we can always consider that the gravitational pressure drop is much larger than the frictional pressure gradient, that we can always assume. So, therefore, for vertical systems with negligible wall shear, non-accelerating flows, under such conditions, if you remember, we had obtained or we had proposed that JGL is a function of alpha only for a particular system. Remember that this had come for, I will write down the conditions here, for negligible wall shear. If you remember, I am just writing it down so that it gets into your head. For negligible wall shear applicable to vertical gas liquid slug flow. These are all with respect to gas liquid slug flow. Under this condition, from drift flux we obtained JGL as well as UGJ. They were function of alpha only for a particular system, isn't it? So, therefore, for vertical gas liquid slug flow we can always say from drift flux model, So, this we can always say yes or no, agreed. So, therefore, we have said two contradictory things. Once we have said bubble dynamics is a function of J only, okay, from slug flow, and again from drift flux we say bubble dynamics is a function of alpha only. It cannot be a function of J. Now, if both of these have to be true, then in that case what can happen? Both of this can be true when UGJ is neither a function of alpha nor a function of J, it is a constant. So, since both the things, you have the slug flow model as well as the drift flux model, they contradict each other. So, therefore, from these two it simply implies that UGJ equals to constant. It is not a function of either J or alpha. Only under that condition only the entire thing can be applicable. Do you agree with me? So, once you can find out UGJ, then we can proceed. Now, what is this UGJ? UGJ is nothing but UG minus J, or in other words it is in this case, since the entire thing rises up as a Taylor bubble, you can write it down as UTB also, UTB minus J. Therefore, we find no matter whatever will be the value of J, your value of UGJ has to be constant. That means, whenever we increase J, your bubble velocity also has to increase, so that the difference is a constant. If that is case, then in that case this should be equal to the bubble velocity at J equal to 0. That means, suppose in a tube we have just water, the water is not flowing, we have just filled a tube with water and we introduce a Taylor bubble inside the tube, then the velocity with which the Taylor bubble is rising, in single Taylor bubble rising through a tube, then that should give me the velocity UGJ, the drift velocity under all conditions of slug flow. Is it correct? So, therefore, we find out a method of finding out the drift velocity. Why is drift velocity important, or why is the bubble velocity important for that matter? Because whenever we want to analyze anything of slug flow, the first thing, anything of two phase flow for that matter, first we would like to know the in situ composition, that is the most important thing. One, for two phase flow we know the in situ composition, we can find out all other parameters. Now, what is alpha for slug flow? It is nothing but Jg by Ug, isn't it? Which is nothing but Jg by Ub in this particular case. So, therefore, if we have to find out alpha, Jg is very simple, it is nothing but Qg by A. We need to know Ub. Okay. Now, what is Ub? We do not know. Okay. So, therefore, we find that Ub, this Ugj, that becomes equal to U infinity at j equals to 0. So, therefore, once we know this, we can find out Ugj. From there, if we know j, we can find out Ub. Once we can find out Ub, we can find out alpha. Do you agree with me, all of you? Agreed. So, therefore, and we find that finding out Ugj, the drift velocity, is very easy. Why? Because this particular velocity, it is constant. So, therefore, if we can measure the rise velocity of a single Taylor bubble in stationary liquid for that particular conduit geometry, for that particular conduit orientation, for that particular conduit dimensions, then that will give me the corresponding Ugj for under that conduit characteristics and that particular fluid physical properties. Fine. So, therefore, the way of finding out U infinity is, now we find it is very simple in this particular case. Okay. So, therefore, we find that Ugj is nothing but equal to U infinity at j equals to 0. Now, here I would like to mention one thing very categorically. So long we have been talking about u infinity. Okay. And in drift flux model also I had shown you that the expression can be expressed as a unique function of alpha in this particular form. What was this u infinity that I had mentioned there? It was the velocity of a single bubble in an infinite medium. Remember, this u infinity and the u infinity which I have used here, both of them are not the same. Okay. This was the velocity of a single bubble in an infinite medium. If you get confused, you can use some other nomenclature for this. This is the velocity of a single Taylor bubble in that particular conduit characteristics. There is nothing infinite medium here, because remember one thing, in an infinite medium we will not have Taylor bubble. Taylor bubbles are formed just because the gas is confined or constrained by the surrounding walls to flow through a definite space. That is why we form Taylor bubbles. Agreed? So, u infinity in slug flow and u infinity in bubbly flow and other cases are completely different, just remember this. Okay. So, therefore, in this particular case what we find that we can find out u infinity, and if we find out u infinity, then we are going to find out ugj, and once we find out ugj we can find out alpha and so on and so forth. Okay. So, therefore, what is the so for finding out alpha, then what do we need? We find that for finding out alpha, it is nothing, as I have told, it is just j g by u g as I had written down, which is nothing but j g by u b, the bubble velocity. And what is the bubble velocity? Bubble velocity is nothing but u g j plus j, is not it? So, therefore, this is equal to j g by j plus u infinity. Agreed? Okay. Why? Because u g j equals to u infinity, and it is easy to find out u infinity. Now, in terms of volumetric flow rates, if we write, this will simply be equal to q g by q L plus q g plus a u infinity. Fine. So, therefore, for ideal slug flow, what do we know? We know that if we want to find out alpha, q g, q L are easily measurable parameters, a is also an input parameter, we need to find out u infinity. This is the first thing. So, therefore, once we can find out u infinity, which is very simple to find out, the experiments are very easy. So, once we can find out u infinity, we can very well find out alpha. Once we can find out alpha, we can find out the pressure gradient and other parameters accordingly. Okay. Now, what are the different methods of finding out u infinity? Now, in order to find out u infinity, remember certain things, that it is the bubble rise velocity in an infinite medium, very sorry, it is the bubble rise velocity in a stationary liquid. Okay. Why does the bubble rise? Due to its buoyancy. So, therefore, the interaction of the buoyant force with the other prevalent forces should give us the measure of how to find out u infinity, is not it? And what are the other forces which are acting on the bubble? What are the other forces which will be acting on the bubble? We assume for the time being the bubble density and the bubble viscosity, they are negligible compared to the liquid density and liquid viscosity. So, what are the other forces that should be acting on it? Interfacial shear, surface tension forces you can say, because generally we have already assumed that the bubble surface is at constant pressure with negligible interfacial shear. Okay, because the curvature is constant and the bubble, its the density viscosity is negligible. So, therefore, viscous forces are definitely one, okay, surface tension forces are definitely one, and definitely gravitational forces are there. Okay. So, therefore, a balance of your buoyant forces with liquid inertia, the viscous forces and surface tension forces should give you an idea of how to find out u infinity. Now, when all the forces are important, naturally the calculations become slightly more difficult, but fortunately for most of the situations we find that one of these forces are usually important. Okay. So, first we will discuss what are the forces, then we will discuss how to correlate these forces with the rise velocity, taking into consideration the dimensionless groups, or what are the different dimensionless groups which we can use to find out the bubble velocity, and then we will discuss the limiting cases when one of the forces become important. Okay. So, we find out the thing which happens is, we know that the bubble rises due to buoyant forces. Okay. And the other forces which are important is, one is liquid inertia, the other is liquid viscosity, the other is surface tension. Okay. Now, balance of liquid inertia and buoyancy, what does it give? If we balance these two, we get a dimensionless group something of this sort, G d rho L minus rho g. Okay. We get buoyant force and liquid inertia, if we balance, we get something of this sort, which I am very sure you have come across across this number earlier. This is nothing but the Froude number. Okay. Remember one thing, when you had talked about Froude number, definitely you had talked about u square by g d or u by root g d, isn't it? We had neglected the density terms. Why? Because we always talk about gas, liquid or air water systems, and for such systems rho g is negligible as compared to rho L, and therefore, they cancel out. So, a balance between buoyancy and liquid inertia gives you this. Suppose a balance between buoyancy and liquid viscosity, that this gives you a number which can be represented in this particular form, d square g into rho L minus rho g. Okay. And if we consider the surface tension and buoyancy balance, this gives us something of this sort. I do not know whether you have come across these numbers or not. This is more or less known as an Yodwas number. Okay. So, this is known as an Yodwas number. Now, for a general solution, what is there? For a general solution, we find that the buoyant force is a function of liquid inertia, liquid viscosity, surface tension. When it is a function of all of them, then all these three dimensionless groups, they become important. And when all the dimensionless groups, they become important, under that circumstances, what we can do is, we can simply solve it by using a graphical technique, where maybe we plot one group against the other with the third group as the parameter. Okay, this can be done. Okay. Now, usually what we would prefer, we want to find out u infinity. So, if u infinity is there in both the x axis and the y axis, then it becomes a problem, isn't it? Then it calls for a trial and error sort of a technique. So, in order to avoid that technique, what we do, we would like to eliminate u infinity from both the groups. So, that u infinity is there either in the x axis or the y axis, and then we would also like to get a group which is completely a function of liquid properties and acceleration due to gravity, which does not have u infinity d, anything of that sort. So, usually what we do, we select one group as this, one group rho L u infinity square by g d into rho L minus rho g. This is one group that we select. Okay. The other group, we eliminate u infinity from both of these, and once we eliminate u infinity from both of these, we get the second group, which is usually denoted as N f. This particular group is obtained by eliminating u infinity from both of them. We get d cube g rho L minus rho g into rho L by mu L, this one whole to the power half. This is the second group that we get. Okay. And again we eliminate both u infinity and d from these groups, and the third group, I do not know whether you have come across that, that is the Archimedes number. Okay. This Archimedes number is sigma to the power 3 by 2 rho L divided by mu L square g to the power half rho L minus rho g whole to the power half. So, therefore, what do we get? We get one particular group. If we plot this versus N f here with the Archimedes number as the parameter, then in that case we get a family of curves from where we can find out u infinity. This is one such type of curve. This is dimensionless bubble velocity. This is the Froude number. In this case, the dimensionless inverse viscosity number N f, which I have already written down, and this has been plotted with your Archimedes number as the parameter. So, from this particular case, if we know the Archimedes number, you can locate the particular curve, you know the dimensionless viscosity number, you locate the point, and from there, from the y axis, you can find out the dimensionless bubble velocity, which is nothing but the Froude number. Once you can find out the Froude number, you can find out the u infinity as well. Okay. Now, remember one thing, see, you can combine the different forces in different ways, and you can generate a large number of dimensionless groups according to your particular convenience. Okay. So, one particular way of generating and combining them is the one which I have shown. The another very well known way of combining them is again same thing, the Froude number is always used, and that is plotted against the Yodvor's number with a liquid parameter group y as the parameter. It is g mu l to the power 4 by sigma cube rho l. So, these graphs have also been generated. In fact, these graphs are much more widely used as compared to the previous one, just because it is much more useful to use these graphs. In this particular case, this is rho l g d square by sigma. Okay. This is the dimensionless Froude number. We have obtained them from the same previous groups which I have already shown you. From these particular groups itself, by different combination of these three groups itself, we have obtained the set of curves which I have shown here in this particular transparency. Okay. In this particular slide, so here I have shown we can either use these curves, but they are much more spread out, they are not very conveniently used. Usually we use this set of curves where your Froude number has been plotted as a function of Yodvor's number with the liquid property group as the parameter. Okay. Now, we generally find that there is that I will discuss later. Okay. There is one particular analytical expression which can be used if the graphs are not available with you. This analytical expression is something of this sort, K1, which is nothing but this particular group is known as K1. So, this K1, the analytical expression which correlates K1, Yodvor's number, y and all those things, or which correlates the liquid viscosity term, the surface tension term, etc. This is something of this sort, K1 equals to 0.345, 1 minus e to the power minus 0.01 NF by 0.345. This is used when surface tension effects are negligible. We can use, instead of going for the graphical calculation, when we can go for this particular analytical expression as well. Okay. And when surface tension effects are not negligible, then this can be written down as 0.345, 1 minus e to the power minus 0.01 NF by 0.345 into 1 minus e to the power 3.37 minus n Yodvor's divided by m. Okay. So, when all effects are there to incorporate surface tension effects. So, the entire set of the curves which I have plotted down in the transparencies and shown you, a single analytical expression to merge all the curves is this particular expression, and usually surface tension effects are negligible, then we can use this simplified expression when inertia and viscous forces are important. When inertia, viscous and surface tension all are important, then this particular expression should be used, where m can take up different values. These particular values, they are more or less available in textbooks. We find that m, it is a function of your inverse viscosity number which has been named, and usually when NF is less than greater than 250, m equals to 10, you will find these in textbooks. When NF lies between 18 and 250, m equals to 69 NF to the power minus 0.35, and when NF is less than 18 we find M equals to 25. Okay. So, therefore, there are large number of expressions, textbooks give you these expressions for when surface tension effects are negligible. I have told you this is the expression. Again, when viscous effects are negligible, that means for large NF, okay, in inviscid region, under that condition what happens, naturally this term becomes important, this term becomes less important, isn't it, in the inviscid region. So, for under that conditions we can write down K1 it is equal to 0.345 1 minus e to the power 3.37 minus the Yodvor's number divided by 10. We directly take up the value of M as 10, because for large NF means NF greater than 250, M equals to 10. So, therefore, for large NF in the inviscid region, K1 can be taken as this. Okay. Now, remember certain things. So, therefore, what did we do from the beginning? From the beginning we were trying to find out alpha for the slug flow pattern. We found out that alpha can be written down in as this particular expression. In order to find out alpha, we need to find out u infinity. Now, in order to find out u infinity, naturally we have to go for a force balance. What are the forces which are important here? Definitely your buoyant force is important, gas rises due to the buoyant force. Apart from that, liquid inertia is important, liquid density is important, liquid density is inertia, liquid viscosity is important, surface tension is important, but gas density, gas viscosity we can neglect these. Okay. Now, if these forces are important, then naturally the buoyant force will be interacting with these forces and then enable the bubble to rise, isn't it? When we find that inertial forces are important, then naturally we find that a balance of buoyant force and inertial force is represented by a Froude number type of expression. When viscous forces are important, then the balance of buoyant and viscous forces gives you a sort of an Yodvor's number or something. It is not exactly Yodvor's, it is the inverse viscosity sort of a number which becomes important. Okay. And when surface tension is important, then this particular number it becomes important. Okay. Now, there are circumstances usually for air water systems in ordinary pipes, liquid inertia is important, comparatively viscous and surface tension forces are negligible. When that happens, what happens? Only this particular group is important, the other groups are not important. In that case, what happens? Naturally this must take up a definite constant value, isn't it? So, for only liquid inertia being important, what do we have? When only liquid inertia is important, under that condition inertia dominant. Okay. Under that condition, your rho L u infinity square by g d rho L minus rho g, this naturally becomes a constant which is given as K1 in this particular case. Okay. Now, usually people have found that this particular K1, so therefore, u infinity it can be obtained as K1 root g d rho L minus rho g by rho L, and usually when gas liquid systems, these two cancel out, it is just K1 root g d. Unless you know K1, you cannot find out u infinity. People have found out that K1 is a constant, and for round vertical tubes a value of 0.345 can be taken. This particular value of K1, this depends upon the, naturally it should depend upon the conduit shape. Okay. For round vertical tubes it is 0.345. For rectangles, for annulus, some work has been done. People have found that usually for rectangles your K1 it is a function of the larger shorter length by the larger length, and in that condition this particular diameter has to be replaced by the larger length. Okay. These things people have found out, and they have found out for rectangular channels. Say for rectangular channels, K1 it is a function of ds by dB. Okay. And under that condition it can be written down as 0.23 plus 0.13 ds by dB. Okay. Again, for annulus, what people have found? For annulus, people have found K1, it is a function of the, again the inside diameter by the outside diameter, and u infinity is given as K1 root g d0. In this case also your u infinity is given as K1 root g d bigger. Usually people have found those things, and this particular K1 is given by this expression. Here also the K1 it is a function of d1 by d0, and certain expressions have been proposed for people. And interestingly, in the annulus, what people have found that as your d1 increases, K1 increases, okay, or do decreases, K1 increases. That means, as the passage becomes more constricted, your K1 increases, or in other words, the bubble rises at a faster rise velocity when the annular gap it decreases. Okay. So, this was for inertia dominant situations. Now, when viscous dominant situations are there, for viscous dominant situation we find when viscosity is dominant, under that conditions naturally the second group is going to be important, and that is going to assume a constant value, isn't it? So, for such situations what do we find? We find u infinity mu L by d square g rho L minus rho g, that becomes a constant which is usually given as K2. Okay? Or in other words, for such situations your u infinity can be obtained from K2 d square g rho L minus rho g by mu L. For this K2 value, it is almost equal to 0.01 or maybe say 0.0096, some sort of this value is obtained for K2, correct. And when surface tension is important, what happens, can you tell me? Inertia dominant, I have already told you, this particular group becomes important. Okay? I have already told you. This is a Froude number, this becomes important. When viscosity is dominant, this particular group becomes important. When surface tension is dominant, naturally the last group has to become important. But what happens when surface tension becomes important? Will the bubble move at all? See, one thing, its shape is governed by the containing cylinder. If particular the conduit is quite small, the bubble volume is very large, it cannot be a sphere under that particular conditions. Okay. So, therefore, what will happen if the surface tension is large, it will prevent the bubble from rising. So, the bubble does not rise at all under these conditions. Okay. So, when your surface tension becomes important, under that circumstance we find that g d square rho L minus rho g by sigma, this particular group which I had written down here, this particular group naturally sigma becomes very large. So, therefore, the inverse of this, which is nothing but known as the Yodworth number, this becomes small. So, therefore, surface tension dominant condition, your surface tension dominant, that happens when Yodworth number value is less than 3.37. Under this condition, the bubble does not rise at all. Is it clear? So, when inertia is dominant, Froude number is important. When viscosity is dominant, one type of particular number is important. This number we do not use much. Instead of this number, we use the inverse viscosity number. Okay? And when surface tension is important, the bubble does not rise at all. If the surface tension becomes so important that the Yodworth number becomes less than 3.37 or less than 4, then the bubble does not rise at all. And when more than one forces are important, then actually when inertia and viscous forces are important, under that particular conditions, I have already given you the expressions here. When inertia and viscosity, your viscosity and your inertia is important, this is the expression. When inertia and surface tension is important, this is the expression, and when everything is important, then usually this is the expression that we use. But normally we do not use these analytical expressions, we prefer to use the graphs which I have already shown you. Okay. These graphs, using these graphs, if we know the Yodworth number, we know the liquid property group value, they are very easily found out, we can find out u infinity. And once we find out u infinity for the particular condition, considering the forces which are important under that particular conditions, we can find out your alpha, and once we can find out alpha, we can find out the pressure drop and other things. Okay. But remember one thing, the u infinity that you have found out in this particular case, u infinity is fine, it is the velocity of a single bubble in a stationary liquid. But using this u infinity, the u bubble which you are trying to find out, that u bubble, it is not a function of u infinity only, it is a function of j as well. Okay. So, therefore, it is also influenced by certain other parameters and it needs further modifications for accurate estimation. So, tomorrow we are going to do the additional modifications which we shall be introducing in order to get a modified expression of the bubble rise velocity for the slug flow pattern in vertical tubes. Thank you very much.